Our next speaker is Gregg from Queen's University and RMC, and they're going to talk about binary stars or evolutions, binary evolution.
Excellent. Thanks very much. Good morning, everyone. Thanks for being here, particularly on the morning after the banquet. Pleasure to see you. So much of my research is driven by the need to exploit stellar magnetic fields as probes of stellar internal structure and evolutionary histories. I tend to use intermediate mass and high mass stars in this regard because of the fundamental changes in internal structure that they undergo as they evolve from the main sequence across the HR diagram, and because they end their lives as a variety of very strongly magnetized remnant objects. Today, I'm going to be talking about another facet of this work. I'm going to be talking about the fact that many massive stars live their lives in binary systems. I'm going to be exploring proposals that suggest that magnetic fields in massive stars, as we've heard a couple of times during the course of this conference, may be generated at least in part by the mass transfer and merger interactions that take place in those systems. We believe that those interactions are actually remarkably common. We've known for a little over 10 years that more than 70% of massive stars are likely to undergo an evolution in a binary system, either through merger or mass transfer, that's going to fundamentally modify its characteristics. And we've known for a few years that MHD simulations are able to generate powerful magnetic fields when they attempt to reproduce the dynamic processes that are at the root of binary interaction, mass transfer, and mergers. So what I'm going to tell you about today is the story of two recent discoveries with the most powerful magnetic machine on the planet, Espinal, discovering magnetic fields in two objects that we believe to be the remnants of both mergers and mass transfer in massive binary systems. Start out with this particular object. So this is HD 45166. The system itself has been known for quite a long time. It's actually a composite system that is composed of a so-called quasi-Wolf-Rayet star because of its superficial similarity to the spectra of Wolf-Rayet stars, although physically very dissimilar, as well as a main sequence B-type star. And these two objects are, in fact, in a bound system. They orbit around one another in about 27 years. And recent observations show that the two objects actually exist at positions that are predicted by evolutionary and binary models. So this is a system in which we have a very peculiar object, this quasi-Wolf-Rayet object, and a main sequence B star, an object that presumably we understand quite well. The objects are sufficiently far apart that they've never interacted with one another, and so we can use the B star as a probe of the timescale and chemistry of the evolution of the system. When we look at the physical properties of the two objects, the B star that you can see on your right is about a 13 kilokelvin object, sits in the early main sequence and has chemistry as one would expect from an unevolved star. On the other hand, the quasi-Wolf-Rayet star, from modeling the spectral energy distribution and its spectrum, is very different. It's an object that has a very low mass, about 2 solar masses, but an extremely high temperature, and this is what gives rise to its very peculiar spectrum. The only explanation for the physical properties of this object is that it's a so-called strip star. It's the remnant of an object that's undergone binary interaction, removing its outer layers and revealing the hot, chemically processed interior of the object. And over the past 5 years or so, there have been a number of these objects that have been confidently detected in the galaxy, and this is one of them. We're able to model the evolution of this particular object using binary stellar evolutionary models in one dimension. And we believe that this particular quasi-Wolf-Rayet star, this strip star, evolved from the evolution of a short period, 2-day, intermediate mass binary system consisting of a 5 and a 3 solar mass star. Those two stars in-spiraled and merged to generate the object that we see today. Throughout all of this action, the B star in its 27-day orbit was unaffected. So this system comes to our attention because it was suggested by my collaborator Tomer Shinar that the variability that we see in the emission lines of the quasi-Wolf-Rayet star, the strip star, is actually due to the fact that the object is magnetized. And so we observed it with Espinal, and we detected extraordinary Stokes V signatures in all of the lines in its spectrum. The lines that you're seeing here are all lines that are produced in the spectrum of the very hot strip star. The B star itself has no magnetic field to speak of. The magnetic field in this star is sufficiently strong that it's able to split both emission and absorption lines in its spectrum into Zeeman components, and we're able to measure the modulus of the star's magnetic field. It's over 40 kilogauss, making it the strongest magnetic field ever detected in a non-degenerate star. Because we believe this to be an object that is spending the last phases of its life in this phase with a revealed magnetic field that's so strong, we believe that this object will eventually evolve and become a neutron star. And because of the strength of its magnetic field, we've proposed that it's likely to become a magnetar. So in the second half of the presentation, I'd like to talk about a new result that we haven't published yet. This relates to a well-known object, Plaskett star. Plaskett star is a binary system. It was discovered in 1922 by our own John Stanley Plaskett at the Dominion Astrophysical Observatory. And in this particular situation, we believe we've discovered a system in which mass transfer in a binary system has generated a magnetic field. The radial velocity orbit of Plaskett star is well known. The two stars orbit around one another in about 14.5 days. There's a so-called narrow line component, which has relatively sharp spectral lines, and a broad line component. You can see both of them in the spectrum. These are two observations obtained with Espinal at two phases of quadrature of the orbit. You can see the narrow line component moving back and forth on top of the very broad line profile of the broad line star. This system comes to our attention because the broadline star is magnetic. It was discovered to be so by Jason Grunhut during the MIME survey back in 2011. The star itself exhibits a variable longitudinal magnetic field with a period of 1.2 days. That's the star's rotational period. And magnetic maps of the stars that Colin Folsom computed recently demonstrate that the magnetic field is a dipole, and it's been stable over the last 15 or 20 years, which implies that the magnetic field is a fossil magnetic field, similar to those that we see in other intermediate mass and high mass stars. One of the interesting outcomes of the study by Jason and Colin was that they weren't able to reconcile the motion of the circular polarization profiles in the lines of the broadline star with the previously reported large radial velocity variations of the broadline component. And what's going on here is that the circular polarization provides us with a unique window into the properties of the magnetic component of the system, completely removing any impact from the narrow line non-magnetic component. And that allows us to resolve a number of ambiguities related to the measurement of the velocities of the two stars that had been inherent in all of the studies in the past. And so what this has let us do is make fundamental changes to our understanding of the structure and the evolution of the system. In particular, what we've been able to do through analyzing the spectrum and the spectral energy distribution of the star is to infer that one of the spectral lines in the spectrum of the star, in particular a triply ionized oxygen line, is formed only in the atmosphere of the broadline star due to the chemistry of the system. And so we've been able to remeasure the radial velocities of the two components. Thank you very much. What we're seeing here in red are the radial velocities of the narrow line star, which is exactly the same as it's been measured since 1922 by a number of observers. But in green, we see the new measurements of the radial velocities of the broadline star. And instead of showing an amplitude that's comparable to that of the narrow line star, what we see is that the amplitude is very small. For those who study binary stars, we're able to recover the orbital period from both of these data sets. And of course, the phasing is what you'd expect from two stars that are in orbit around one another in a 14.4-day orbit. So the basic takeaway from this, because the amplitude of the radial velocities has changed substantially, our understanding of the mass ratio of the system has changed substantially as well. In particular, we now know that the narrow line star needs to be at least 5 times less massive than the broadline star in order to satisfy these radial velocity constraints. Coupling that with the fact that the two stars are similar temperature and similar luminosity, again, the only explanation for the physical properties of the narrow-line star is that it's a stripped object. In this particular case, the scenario that we're developing is that the two stars have evolved from a system with initial masses of about 18 and 16 solar masses. The narrow-line star filled its rush low and transferred matter onto the surface of the broad-line star, generating the star's magnetic field in rapid rotation, leaving us today with a roughly 6 solar mass narrow-line strip star and a 30 or 40 solar mass broad-line star. So I'm going to skip directly to some final words. So the basic takeaway from this presentation is that Espadon is providing the first true observational constraints on proposals that magnetic fields are generated through binary evolution by processes such as mass transfer and mergers. I think we've published the first two truly convincing results. But what I want to leave you with is the fact that Espadon and, by extension, Winiakeo will provide a capability for continuing the systematic exploration of stellar magnetism throughout the HR diagram and discovering new objects like this over the next decade. So with that, I'll finish up. I'm going to put this up, and if people have questions about what they're seeing on the screen, I'm happy to answer them. But thanks very much for your attention.
Well, let's talk. Any questions for Gregg?
Well, then I'm going to be the person that asked you about this.
I love that. Thank you so much. So over the past couple of years, I've been working with Indigenous colleagues at Queen's University and RMC to develop methodologies for knowledge transfer using traditional beadwork practice. And so what you're seeing here on the screen is the development of a maquette illustrating the mass transfer history of Plaskett star system and the generation of its magnetic field. We actually developed this because I wanted to be able to explain the physics of the system to young children, and they were having trouble with the MESA one-dimensional evolutionary diagram. So this actually helped a lot. But it's a very interesting method for sharing relatively complex knowledge with communities and bringing it to where they are.
Any other question? I'll take a quick one. Can you estimate roughly how many of these strip stars we're expecting to target for Espadon, like a magnet level?
Yeah, so currently we know of perhaps a half dozen. We have one in the queue to be observed during the next semester with Espadon. It's not proposal number C0001 though. It's a later proposal. And the surveys that are currently ongoing are discovering more of these objects as they go. The issue is, of course, that they're relatively faint. So we're really pushing a 3.6 meter telescope, notwithstanding the fact that it's the best one on the planet, to its limits.
Okay, cool. Thanks. If there's no more questions, here's one.
Thank you, Gregg, for this nice presentation. If you go back to the first object you've seen, this fake Wolf-Rayet stars, I was wondering where are coming from the emission lines. I believe they have to come very close to the star for being able to detect such a strong magnetic.
So this object is truly a cinder. It has a radius of about 1 solar radius. It has a mass of about 2 solar radii and an effective temperature of 55,000 Kelvin. And so the emission lines, we believe, are being generated in the star's wind, which is probably magnetically confined by the 43 kilogauss magnetic field. So we think we're seeing evidence for a magnetosphere. We're performing monitoring in order to be able to model that.
Okay, let's thank our speaker again.